right, ladies and gentlemen, this presentation is on mathematically determining the order of individual reactants from that doing multiple trials, changing concentration and measuring initial rate. And the reason that I'm including this slide is because almost all the examples we did in class had what I call nice, neat, and pretty values, where it was a very, very clear doubling of the concentration, and then followed by a very, very clear quadrupling, for example, of the rate. And this presentation, this talk is about what do you do when you don't have nice, neat, pretty, clean data? What if it's much less apparent what factor the concentration is going up by or what factor the rate is going up by? Then what do you do? How can you still figure out order even if your data isn't clean and perfect? And the strategy is very, very similar to what we were doing in class in terms of writing that rate law. Like we were doing, like I said, if you double, then the rate, put rate doubles, concentration doubles, what exponent does that reactant have to have? It's a very, very similar idea. You want to start by writing a rough rate law for your reaction, and just what Mrs. Julian calls a rough rate law is essentially just writing your rate law with x and y as the orders, having everything else, rate equals k times the concentration of A raised to the x. That would be a rough rate law because you just don't know what number that x is. And then the key is about comparing two trials. You have to look at two trials. Just like before, you still have to look at two trials. But the way that we're going to compare it now that our numbers aren't neat and clean and pretty, is you're truly dividing one rate law by another. So it's all going to be in fractions. One rate law divided by a second rate law. And what that allows us to do is to compare. That's what that dividing one rate law by the second rate law is letting us do. We're comparing. And it's not though just setting up rate law 1 or rate law 2 divided by rate law 1. You have to plug in. Because the point is that we're trying to figure out what the exponents are, but our data isn't obvious. So you have to plug in the data that we do have so that we can do a little bit of math and get to the point where it is obvious. And the examples I'm doing, I found from multiple sources. I'm not actually doing sample exercise 14.4 in the book, but sample exercise 14.4, it walks through this entire process. Everything that I'm about to say, it goes through that as well. It shows you how you can mathematically prove a rate law if your data isn't apparent. I'll also add that you could use this technique to determine reaction order even if it is apparent, because maybe this makes more sense to you than explaining it with words. So our first example, for the reaction x plus y goes to z, determine rate law from the following data table. And we've got trials 1, 2, 3, so I'm just going to add that in. And here is a case where we don't have nice, neat, clean, pretty information in our data table, and how we really will have to rely on this mathematical proof. We've got x and we've got y. When I look at this data table, the first thing that I notice is trials 2 and 3, and I notice trials 2 and 3 because the concentration of the x is not changing between trials 2 and 3. That means that when I'm trying to figure out the order for x and I'm trying to figure out the order for y, I want to figure out the order for y first. Because I can actually use what we've already discussed in class to figure out the order for y. Because I do have information about the x where the x is staying the same. So trials 2 and 3. So looking at everything that's going on between trials 2 and 3, the concentration of the y doubles when we go from 2 to 3, right, 0.3 to 0.6 molar. The rate doubles, 0.127 to 0.25. I mean, that's a doubling. It's not a perfect doubling, but that's pretty darn close. That's close enough for us. Rate doubles. So it's first order in y. So I'm saying that right now because I'm going to erase that information, but that's really, really useful. We're going to need that. So y is first order. And do notice that that is the first thing that I zeroed in on when I looked at this data. I noticed that I do have two trials where the concentration of x is the same, which means that I can use those two trials to figure out y. And that was the first thing off the bat that I did. Okay, so we figured out the order for y. Now, figuring out the order for x. x, it's harder because look at our 3 concentrations of y. I don't have 2 trials where the y is not changing. I just don't have that data. We can still figure out the order for x, but here's where we have to mathematically prove it. So going back to that strategy that I said on the previous slide, what do we need to do? We need to basically write rate laws and then divide them by one another. Essentially, we're going to compare 2 of the trials. So what do I mean by that? The trials that I want to look at for x, hopefully you can figure out that in order to figure out the order for x, I have to look at trials 1 and 2. Well, I don't have to do trials 1 and 2. I could do 1 and 3, but I can't do 2 and 3. I have to do either 1 and 2 or 1 and 3 because I don't want to use these 2 because the x is staying the same. I want to pick 2 trials where x is changing. You could do this with 1 and 3 as well, and you'll arrive at the same result. But I'm going to do 1 and 2. So how do you prove it mathematically? Rate 2. But when I say rate 2, I mean trial 2. I'm writing out a rate law. X to the x, we're trying to figure out what it is, times the concentration of y to the first. I've already figured out that y is first order, so I'm basing this off of information that I've already done. I am now going to divide both sides by the rate law based on trial 1. Rate 1 equals k times x raised to the x times y to the first. What I've done is I've written a rate law for trial 2, I've written a rate law for trial 1, and I am dividing them. This is allowing me to compare basically the data that's in trials 1 and 2. And the reason that I'm doing trial 2 divided by trial 1 rather than 1 divided by 2 is because I look at the rates right here, and I see that the rate in trial 2 was larger, and I basically, it's like dividing 2 over 1 rather than 1 divided by 2. It's easier, at least for Mrs. Julian, to work with values that are larger than 1. You'll get the same answer if you work with fractions. You can still figure it out, but I think it's a little bit easier for me. So I'm doing the larger number divided by the smaller number. I am now going to plug in numbers from the data table. But before I do that, before I plug in numbers, I want to get rid of things that are the same. And basically that's the value for k. K is a rate constant. It doesn't matter if I'm doing trial 2 or if I'm doing trial 1. K is going to be the same regardless. But everything else I'm going to use. So I'm going to be using these 2 numbers for the concentration of x, these 2 numbers for the concentration of y. And I'm just going to plug right in. So plugging in the values from the data table. 0.127 was the rate divided by 0.053. Now I got rid of k because it's a constant now. What's the concentration of x in trial 2? The concentration of x in trial 2 is 0.2, and I'm raising that to the x. Concentration of y is 0.3. That's to the first. That's just 0.3, so I'm going to leave it as that. Divided by, and then trial 1. The concentration of x in trial 1 is 0.1. Raise that to the x, and the concentration of y in trial 1 is 0.5. This is going to allow me to calculate x. I will be able to solve for x based on this comparison, because at this point it's just doing math. So, all right, 0.127 divided by 0.053, simplifying it further. This is going to turn into, doing that math, 2.4. Right, divide 0.127 by 0.053, that's 2.4. Now, a little bit of a reminder. Because the y here is raised to the first and the x here is raised to the x, they have different exponents. You have to simplify them separately, right? Math class, you have to simplify them separately. So I'm just gonna basically dividing my fraction into two components. So this is 0.2 to the x over 0.1 to the x, and then I'm going to do 0.3 divided by 0.5 because they have the same exponents, so I can divide them. 0.3 divided by 0.5 is 0.6. This is what I have at this point. 2.4 equals 0.2 to the x of 0.1 to the x times 0.6. Because 2.4 its exponent is 1 and 0.6 its exponent is 1, I can, it's combined like terms. I'm going to divide both sides by 0.6. I can't touch this section with 0.2 raised to the x because it's got a different exponent, right? And that is the idea. It has a separate exponent, so I can't simplify it the same way. So I'm going to do that above. So 2.4, let's see, divided by 0.6, divided by 0.6, and I get 4. 0.2 to the x over 0.1 to the x. And again, this is math class. I mean, this is no longer a question of chemistry. This is a can you solve for x sort of a thing. Because they each have the same exponent, I can simplify in terms of the fraction. It becomes 0.2 divided by 0.1 raised to the x. So this is going to become, so 0.2 divided by 0.1, that's 2. But I haven't gotten rid of the x yet, so that's raised to the x. Well, now it should be very, very apparent what the power for x is, because there's only one way the statement is true. X has to be 2. That means that our x is second order. If you wanted to prove this with words, it would be very involved, because you would have to make a statement about the doubling effect of x. You'd have to make a statement about the fact that the y went down from 0.5 to 0.3, and it gets involved. This tends to be a little bit more direct, mathematical approach. So if I'm just writing the rate law, actually, answering the question, then I would write rate equals k times the concentration of x to the second times the concentration of y to the first. So that's my rate law. And this is the idea. You you divide rate laws for different trials. You plug in numbers and you solve for the exponent. I'm going to go through a second example as well. For the reaction 2NO plus Br2 yields 2NOBr, determine the rate law from the following data table. And we've got 4 trials in this case. 1, 2, 3, 4. Once again, when I see this, my eyes, when I'm looking at this data, I see a couple things. I see the fact that, okay, I've got 0.1 and 0.1 for the NO between trials 1 and 3, so that's good. I see that I have 0.2 and 0.2. That's the same right there. That's good. And I see that I have 0.5 and 0.5. That's good. But when you expand it, for example, if we're looking at the NO, yes, between trials 1 and 3, the NO stays the same, but the concentration of Br2 from 0.2 to 0.5, that's not an obvious doubling. That's, going up by a factor that's less clear. And ditto, if we look at, for example, in the other direction, if we're looking at these two, trials 3 and 4, where the concentration of Br2 stays the same, well, yeah, it stays the same, but the concentration of the NO is not doubling, it's not quadrupling, it's not a nice, neat, clean, pretty value. So if you have numbers like this, a mathematical approach will always work regardless, and you can fall back on that. So just like any of our rate laws, we're going to take it one at a time. So I'm going to start with NO. And I'm going to use, in order to figure out the order for NO, I'm going to use trials 1 and 2. I could use trials 3 and 4, but we're picking these two trials because the concentration of the bromine is staying the same. It's not changing 0.2 to 0.2. You could use trials 3 and 4 as well and figure it out that way. I happen to do the math with 1 and 2. 3 and 4 is also an option. All right, and we're going to do exactly what we did in the last one, meaning write two rate laws, divide them, and simply solve. So I'm going to do rate 2 divided by rate 1 equals k times NO to the x times Br2 to the y. That is a y. K over NO to the x, Br2 to the y. Again, this is exactly what you did last time. You're simply writing two rate laws and you're dividing them, and I'm dividing 2 divided by 1 because the rate is larger in trial 2 than it is in trial 1, and I kind of like to do larger divided by smaller. get rid of the K because it's going to be the same regardless, and then plug in your numbers. So straight from the data table, the rate in trial 2 is 150, the rate in trial 1 is 24. NO, I'm sorry, I'm going to deal with the BR2. You could plug in, well, I'll deal with that. I guess I'll write it out a little bit more discreetly. The concentration of NO in 2 is 0.25. Notice I got rid of the square brackets. Square brackets indicate concentration. If you're plugging in, you no longer need them. To the x over 0.1 to the x, and then it's going to be times the concentration of BR2, which is 0.2 to the y over 0.2 to the y. You can get rid of these. In fact, you need to get rid of these because they're the same. 0.2 to the y divided by 0.2 to the y. That cancels out. You get rid of that. That goes away. And now it's math. It's solving for x. You can do that. 150 divided by 24 is 6.25. And again, they have these two things have the same exponent, so you can simplify by simply dividing 0.25 by 0.1. 0.25 divided by 0.1 is 2.5, but you haven't gotten rid of that exponent. That exponent is still there. And if, by the way, I will also add that if you're unclear how I get from the 150 divided by 24 equals 0.25 over x over 0.1 to the x to this final step that I've written, that's a math lab issue. Make sure you go to the math lab and you understand how exponent rules work. 6.25 equals 2.5 to the x. You need to be able to solve for x from this point. Again, this is a math issue. You need to hopefully understand that in order for this statement to be true, x has to be 2. It's only if you square 2.5, you get 6.25. So we have second order for the NO. Okay, so that takes care of the NO. We figured out that it's second order. And now we're going to do the exact same sort of thing. We're going to figure out the order for the BR2. And just like before, I don't have neat, clean data necessarily. So for the BR2, so I'm going to have to do it mathematically for the bromine as well. I'm going to use trials 1 and 3. And I'm using trials 1 and 3 because despite the fact that I don't have neat, clean data, I do see that, okay, the NO is staying the same. Because I've now already figured out the order for the NO, realistically, I could pick any two trials where the concentration of the bromine changes, but it is a little bit easier if you have the option. Pick the option where it does, in fact, stay the same. Right, so I'm picking this because the NO stays the same, but the bromine changes. Same idea. Right, two rate laws and simply divide them by one another. The division allows you that comparison. It's like when we do empirical formula problems, you divide by the smallest value. You're comparing mole ratios. That's what you're doing. So I get K NO to the second over BR2 to the Y. I'm trying to figure out what the Y is. I've already figured out the order for the NO. I've already figured out that it's 2. And then you plug in. I'm going to get rid of the K right now because it's the same. I'm also going to go ahead and get rid of the NO squared because 0.1, 0.1, it's going to be the same. I'm just going to skip that step. And then plugging in the data, I have 60 divided by 24 for the two rates. Concentration of bromine, I have 0.5 to the Y over 0.2 to the y. And then it's really just a matter of solving out. 60 divided by 24 is 2.5. 0.5 divided by 0.2. You can do 0.5 divided by 0.2 because they're both raised to the same exponent. They're a like term. So 0.5 divided by 0.2, that is 2.5, but it's 2.5 to the y. You're keeping that exponent there. All right, well, what value does y have to be? This is pretty clear at this point. Y has to be 1. So it's first order with respect to the bromine. So if we just simply close out the problem, determine the rate law, it's just putting everything together. Rate equals K times the concentration of NO squared times the concentration of Br2 raised to the first power. So this idea of using math to prove to determine order, it's simply about comparing rate laws, dividing the rate law for one trial by the rate law for the other trial, and you're canceling like terms, simplifying like terms, and solving for the exponents. That's the best way about it. And again, these examples, I picked these examples because we don't have neat, clean, pretty data, and sometimes it's rare, but sometimes that does happen. So you need to be able to understand how, if it's not a clear doubling or cutting in half or tripling, what to do. What to do when it goes up by a factor of 2.4. How you can still prove it, even beyond a simple explanation.